Good day, viewers. You're welcome to yet another broadcast of Science Spectrum with Dawn. And of course, if you're new to the channel, you may want to follow me on Facebook on the page Academic Global Streams. Academic Global Streams. Global Streams. Global Streams. And of course, this is tailored to keep you up to speed with relevant topics you might find interesting to watch. All right, so back to business. This is Chemistry Classic. And of course, I'll be talking about the mole concepts. The mole concepts, but not just the mole concept. I'm talking about the relation between the mole and of course with number of entities. I'll talk more about that in a moment. Number of entities of either an element or a compound. So let me talk about the mole concepts. The mole concepts. Mole concepts. Mole concepts. All right. Now, in real life, when we talk about number of units of a thing, it doesn't, this could be a dozen eggs, or a dozen cars, or a dozen crates. So a dozen is exactly 12 units of an object. 12 units of an object. Of any object. That's a dozen. A score is exactly 20 units of any object, regardless of what their masses could be. And of course, a gross is exactly 144 units of any object. And of course, a rim. Take for instance a rim of paper. So one rim is exactly 500 units of that object. But in chemistry, we don't count in dozen, neither do we count in score, nor gross, nor rim, which have their unique values. But we count in a unique value, which we call the mole. So one mole is exactly Avogadro's number, and that's 6.023 times 10 raised to power 23 entities. 23 entities. These entities could mean the number of atoms, how many atoms, number of atoms. This number of atoms of an element is a mole. If it were to be a compound, then you say it's you have a cluster of atoms, which we call a molecule. So this could be number of molecules for a compound. This magic number of molecules of a compound is exactly a mole. And of course, if it's very certain that we are to be electrically charged, it could also be the number of ions. This magic number you see here, we call this Avogadro's number. Avogadro's number. Avogadro's number. This was named after Amedeo Avogadro. All right, so let's proceed. So this is how we count in chemistry. Not in this, but in mole, which is this magic number. All right, so let's proceed on. Now, I want to draw the picture of Niels Bohr's model of an atom, just for the sake of emphasis. So, an atom has a core. This is called the nucleus of the atom. And in this nucleus, you find some amounts. Let me use the symbol N for amounts. So you find some amounts of protons there. In the nucleus, the protons are positively charged. And of course, you could also have you have the number of some amounts of neutrons in the nucleus there. Neutrons do not have any charge. So these particles, we call this the nucleons. And the nucleons are found in the nucleus of an atom. All right. So since the protons are positively charged and neutrons do not have any charge, they have a zero charge. So it means the net charge, the baryoid charge on the nucleus, must be positive. Then you have a cloud around the nucleus where you find some amounts of electrons, some amount n number of electrons which are negatively charged. All right, now the typical size of the atom, and I want to compare the equal size of the atom to the nucleus itself. The size of the atom is exactly, that's this void, you see, is exactly 10 raised to the power minus 8 centimeter. But the nucleus is 100 times smaller, 100,000 times smaller than the size of the atom. So if we scale this ratio 1 to 100,000 to 1, so this should be exactly 10 raised to the power minus 13 centimeter. So you are free to call this centi, by the way, is this subscript centi is 10 raised to the power minus 2. And of course, if we go with the unit of meter, you could also call this centi means 10 to the minus 2. So 10 to the power minus 8 times 10 to the power minus 2 gives us 10 to the power minus 10. That is called an angstrom. So this is 10 raised to the power minus 10 meter also. This term is called an angstrom. So this is the size of the atom. A typical atom is an angstrom. And of course, the size of the nucleus, this is centis, this term. So minus 13 plus minus 2 gives you minus 15. So this is also the same as 10 raised to the power minus 15 meters. So this is exactly 1 femtometer. 1 femtometer, and this is 1 angstrom. So the nucleus is 1 femtometer, and the atom itself is 1 angstrom. Alright, though this is non-SI unit. Alright, so let's proceed on. Now, the mass of the proton is approximately the same as the mass of the neutron. That's, you take per 1 of it from the nucleus. And this value is exactly 1.674 times 10 raised to the power minus 27 kilogram. Now, if you take 1,839 electrons and you sum their masses, it will give you exactly the mass of one proton, which is this value. So the mass of an electron is of this order, 9.11 times 10 raised to the power minus 31 kilogram. Almost insignificantly small compared to the mass of a proton. Alright, so let's go. So this is just the overview of how an atom looks like. And of course, electrons, they jump from one energy level to another. So I'll talk about that when we discuss atomic structure in detail. Alright, so I want to rub this off. Alright, so if you're watching, you may take a screenshot of this. Alright. Now, if I call this atom you see right there, Niels Bohr's model of an atom, though it does have its own shortcomings, because Niels Bohr did say that the atoms spin around the nucleus. But of course, in reality, we've seen that that is not really the case. This spectral lines really tells us that it's not actually what you see happen here. Alright, and of course, the electrons, they are negatively charged. Yeah. So let me just say this. Let me denote charge with the symbol little q. So the charge of a proton, its magnitude, and the charge of an electron, if you take its magnitude, they are the same. Protons do have a plus sign, electrons do have a minus sign, but if you take the values, the magnitudes, the numerical value of their charges, you get exactly 1.602 times 10 raised to the power minus 19 coulomb. This is called not electronic charge, like the text do tell us, but it's called elementary charge because it's also the charge of a proton. So I will use elementary charge for this. Elementary charge. This magic number is called elementary charge because it's also the charge of a proton, not for electron, like you see often electronic charge. Alright, so let's proceed on. So if I call this atom X, I call this atom X, let's give it a name X. Now this could be an atom, let's say this is an atom of an element. So why is a type of matter called an element? It's because the atoms are exactly the same, they're exactly identical in properties. It could be in their density, it could be in their relative sizes, and of course, it could be in even their masses, right? It could be in their masses, even shapes. So if if the atoms of a particular type of matter, they are exactly the same in properties, in their shape, size, and density, that substance is what we call an element. So what an element is a material substance whose atoms are exactly the same or identical. So let's take, this is representing an element now, but this is the atom of an element. All the atoms are exactly the same. Now, If I care to know about the number of protons I have here, the number of protons or the number of electrons I do find in this atom, we give that a name, and of course it has a symbol Z. This symbol, subscript Z, we call this the atomic number. So this is called the atomic number, atomic number, atomic number. And of course this number could be expressed in grams or atomic mass units. I'll talk more about that in a moment. Now, this atomic number is exactly the number of protons or the number of electrons. And if the atom were to be neutral, meaning if you don't see any net charge on it, these two must be the same. Right? And if I had a plus here, let's say I have a certain value of n with a plus here, it means this atom does have more protons than electrons. So it means the number of protons exceeds the number of electrons. That's we call an ion. And in this case, it's called a cation, a positively charged atom. All right. And of course, if the atom had gained, and of course, why would the value be plus? It means the atom had lost some of its electron. But if it had gained, you see a minus here. So it means the number of protons now is less than the number of electrons. So you have more electrons than the protons. This is called a negative ion or an anion. All right, so let's proceed. So now, but we often rule out the number of electrons for atomic number expressed in grams simply because the mass of the electron is way smaller compared to the mass of a proton. So we don't take this into account. So we call atomic number the number of protons. Now there is a superscript here, the number of, we denote that with a capital letter A. This is called the atomic mass number. Called the atomic mass number. Atomic mass number. Also expressed in gram or atomic mass units. It is really the number of protons you find in an atom plus the number of its neutrons. So how many nucleons, how many particles can you find in this atom? That is called the atomic mass number. And of course, this value is always fixed. It's fixed. It's fixed for an atom of an element. It will never change, else it's not that element. But this value could be varied. So this could vary. It could be varied. It could vary. Why? Because the number of protons remains the same, but the number of neutrons could change. So this value could change. So what we do is we take the weighted average. Since this term could change or changes for the same element, so we take the weighted average. That weighted average of the atomic mass number of an element, we call that the relative. We call that the relative atomic weights, or just say it's simply the atomic weights. So it's the weighted average of this number for elements of the same element. So let's proceed. Now, if you take the difference, this term minus this term, you see we are left with number of neutrons, and that changes. Now, by the way, this phenomenon is called isotopy, where you have the number of protons fixed, but number of neutrons do vary. All right, so just for us to have a feel of what this is actually all about. So let's proceed on. Now, so how do we take the weighted average of the atomic mass numbers of atoms of the same elements? All right. So you want to take a screenshot of this while I run this up? All right. Okay. So just one example, and I'll wrap it up for the sake of time. So we'll proceed in our next bulletin. So take for example, by the way, let me talk about the unit here. Atomic mass units. One atomic mass unit, we give that a symbol U, is exactly 1/12 the mass of carbon-12. 1/12 the mass of carbon-12. This is the most stable isotope of carbon, right? You have carbon-11, 12, 13, and 14, but this is the most stable carbon-12. Now, what is the mass of carbon-12? What's the mass of carbon-12? Is exactly 1.9927 times 10 raised to the power minus 23 gram. So if you multiply this term by 1/12, it will tell you what one atomic mass unit is in gram. And this is exactly, so one atomic mass unit is exactly 1.66054 times 10 raised to power minus 24 gram. This is the equivalent statement of one atomic mass unit to gram. Alright, so let me just do a question. Let's see how we take the weighted average of this number you see up here. Alright. So, take for instance that I have an element X, the atom of an element, it's represented like this. And let's say this number you see here, we call atomic mass number. Let's say you have several of this. So let's say this is M1, this is the first atomic mass number. We call it the isotopic mass of an element. So M1, and of course it also does have its abundance. How much of it can you find around you over other isotopes of the same element? That we call, I denote that with an alpha 1. So this is the isotopic mass of the first isotope, and this is its fractional abundance over other isotopes. All right. This product, this and this, defines the isotope of the first element, right? Now, of course, I could have several of them. So I could have M2, the second isotopic mass, of course, is fractional abundance. So, and of course, this will continue on and on like this, right? So the relative atomic weights of an element, say for instance, this element X divided by X, must be M1 times alpha 1, this times this, plus this times this. And of course, I'll keep multiplying this until I get to the last isotopic mass of that element times its fractional abundance. This is how we find the relative atomic weights of an element. So just one example, and I'll wrap it up for this. All right, so we want to take a screenshot of this one and rub this off. All right, so just one example. Take for example, we have chlorine has 2 isotopes. Example given. So let's say chlorine has 2 isotopes. This is its number of protons is always 17. It wouldn't change. This is 37, and let's say this is 35. So I want to look for the weighted average. But I'll give you now the isotopic mass of chlorine. The first isotope, let's say this is 36.96590. This is in atomic mass units. Let's say its abundance is 24.47%. And of course, I give you the mass of the second isotope, which is 34.96885 atomic mass units. And of course, its abundance is not given. But one thing to note is this, is that the fractional abundance of the first isotope plus that of the rest, when you sum everything, it must give you 1.0 if it's expressed in decimal. And of course, if this were to be expressed in percentage like you have here, this would give you 100%. So this value plus this must give me 100% or 1.0 in decimal. So I could convert this to decimal. This turns out to be 24.47%, means I'll divide by 100. So it means the decimal point will go 2 places backward. This turns out to be 0. This is 1, 2, yeah, this is 0.2447. So how do I figure this out? Clearly, the abundance of the first plus the rest, which is just, since I have just 2 isotopes, this must be 1.0 in decimal. So this is given to be 0.2447 plus this we don't know. So all I need to do, I will just make this the solid of the formula. So the fractional abundance of the second isotope of chlorine must be 1.0 minus 0.2447. And of course, if you don't slip up, you get exactly 75.0.75. Check this out. Minus 0.2447. This is exactly, this is exactly 0.7553. This is second fractional abundance. And of course, we are good to go. So to find the relative atomic weight or atomic weight of chlorine now, pretty straightforward, which is, that's unique number you see in the periodic table, which is always in decimal, oftentimes rounded up to whole numbers, is what we're looking for now. So the relative atomic weights of chlorine must be, now I'm taking the weighted average now of its atomic weights, this product. So this would be M1 times alpha 1 plus M2 times alpha 2, since it has just two isotopes. M1 clearly is 36.965 or 96590. Its abundance is in decimal 0.2447. This is in atomic mass unit. I will stick in the unit afterwards. Plus M2, which is 34.96885. Its abundance would be that 0.7553. 7553. And of course, they are all in atomic mass units. So the unit is this. So if you multiply out, it turns out to be that you get, to one decimal place, you get 35.5 atomic mass units. This defines the relative atomic weight of chlorine. All right, I'm going to wrap it up here. Thank you for staying tuned. See you in our next bulletin. Do have a nice day. Bye.